Good day. I'm Norman Wildberger, and today we're going to talk about Leonhard Euler and pentagonal numbers. Euler was the greatest mathematician of the modern age. Originally Swiss, he spent a lot of his life in Germany and in Russia, in St. Petersburg. And he lived in the time 1707 to 1783, during which he contributed to almost all branches of mathematics and established foundational notation, many important theorems, and in fact discovered entire new branches of mathematics. Today we're going to look at how he interpreted the pentagonal numbers that we talked about in the previous video and connected them in a remarkable way with number theory. So I remind you that the pentagonal numbers are this sequence here, and by looking at the table of differences for these, we were able to extend these pentagonal numbers also to sort of negative values. The formula for the pentagonal numbers was n times 3n minus 1 over 2. And last time I posed the question of whether these numbers over here, sort of fictitious pentagonal numbers, whether they play an important role. And Euler showed that they did. He considered putting the proper pentagonal numbers together with these other ones into a single sequence. And he observed that the differences formed by this sequence were rather irregular and did not have an easily understood pattern. So even back then in the 18th century, Euler was aware of the importance of looking at a table of differences. And what I've done here is I've just circled in green the proper pentagonal numbers that actually come from geometrical figures. Now let's take a little diversion to a little bit of elementary number theory. And I'm going to explain to you an important function of a natural number called sigma of n, which is the sum of the divisors of n. So a divisor of a natural number, like 6, is another natural number that divides it. 6 has divisors 1, 2, 3, and 6 itself. And sigma of 6 is defined to be the sum of all these divisors, which in this case is 12. Here's a table of the values of the sigma function for a natural number n. It's a rather interesting pattern which doesn't have a clear structure. We can see the primes reflected by the fact that if you take a prime like 7, then its sigma will be 1 more than it, because it only has 2 factors, 1 and itself. Also, 6 has the rather remarkable property that its sigma is exactly 2 times it. That's what is known since ancient times as a perfect number. Alright, so there's n, there's sigma of n, and a natural question is, how could you calculate this? How could you extend this table without actually factoring a number and counting up the sum of all of its divisors? And Euler discovered a beautiful way of doing just that. So Euler discovered a recursive formula for the sigma function, which means that the value for any particular n can be expressed in terms of values for smaller natural numbers. And here's the relation that he found, that sigma of capital N could be written as a sum of sigmas of smaller numbers. Explicitly, sigma of n minus 1 plus sigma of n minus 2 minus sigma of n minus 5 minus sigma of n minus 7, and so on. What are these numbers that are appearing here that we're subtracting from n? They are exactly the generalized pentagonal numbers in the sequence we wrote down on the previous slide. 1, 2, 5, 7, 12, 15, 22, 26, and so on. There's also the issue of signs. Some of them are plus and some of them are minus. Well, the rule that Euler stated was that if you look at the pentagonal number that you're considering subtracting, let's call it p sub n. So if that n is an odd number, then Euler says we put a plus sign in front. And if n is an even number, we put a negative sign in front. In this sum, there are only finite number of terms because we agree that the sigma function is only defined for terms with positive values. So once what's inside here becomes negative, we ignore it. And there's one more convention, that if we end up with a sigma of 0 as the last term, we must interpret sigma of 0 as equaling n, the number that we started with. All right, so let's illustrate by calculating sigma of 12. So we subtract 1, so there's sigma of 11. We subtract 2, sigma of 10. We subtract 5 with a minus sign. We subtract 7 with a minus sign. We subtract 12 with a plus sign. 12 minus 12 is 0, so this sigma of 0 has to be interpreted as the number 12. And these ones here we can look up in the table if we have all the values up to 11. Sigma of 11 is 12, sigma of 10 is 18, sigma of 7 is 8, sigma of 5 is 6. And so the formula says that sigma of 12 is the sum of these things, which is 28, and that is indeed correct. This sigma function is in fact very interesting and important number theoretical function. And I can't resist throwing in a fascinating aside, discovered relatively recently by Professor J.Lagarias from the University of Michigan in 2002. I've mentioned the Riemann hypothesis in an earlier video. I didn't tell you what it was. It's rather complicated if you set it out in the traditional way. So here is his equivalent formulation of the Riemann hypothesis. It's essentially that this inequality is true for any natural number n. And what does it say? It says that sigma of n, the sum of the divisors of n, is less than or equal to h sub n plus log of h sub n times e to the h sub n. What is h sub n? It's this rational number here, the sum of all the fractions, 1 plus a half plus a third, all the way up to 1 over n. Here's another discovery that Euler made having to do with pentagonal numbers. It concerns another function called the partition function, which plays an important role in combinatorics. All right, so without going into a lot of detail, let me just say rather quickly that P of n is the number of ways to partition a natural number n. And by that I mean, here's an example, P of 4 is 5 because if we partition 4, group 4 into blocks, each block consisting of a natural number, then here are the ways we can do it. We can write it as 4, or as 3 plus 1, or as 2 plus 2, or as 2 plus 1, or as 1 plus 1 plus 1 plus 1. And those are the 5 ways of partitioning 4, and so we say that P of 4 is 5. This partition function is an important function in computer science and other things, and it's also rather hard to compute. Euler discovered, again, a remarkable recursive formula for the partition function. And it turns out that it's essentially exactly the same recursive formula as held for the function sigma. So for example, P of 14, to evaluate that, you take 14 minus 1, 14 minus 2, 14 minus 5, 14 minus 7, 14 minus 12. You put plus signs and minus signs in front, just as we did before. And then you evaluate these ones, which you assume you already know. There's what they happen to be. And if we calculate that, we get 135, telling us that the next term would be 135, without actually having to partition 14 into all possible ways. This becomes a much more efficient way of calculating the partition function, and it's still to this day probably one of the best ways of calculating the partition function. Next time I want to talk about another aspect of baby algebra, which is very important for public school and high school mathematics. The issue of identities. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.